How large can the power output of centrifugal thermal to electric energy conversion be? In a previous video, we introduced the generation of an electric field in ionic aqueous solutions under strong gravitational or centrifugal fields. Now, let's estimate the potential power output. From prior derivations, the generated electric field can be expressed as shown in equation 1, reference 1, where E is the electric field, G is the acceleration, m plus and m minus are the masses of the positive and negative ions, respectively, and Q is the elementary electric charge. As an example, let us consider a hydrogen iodide aqueous solution. Assume the generator is a disc-shaped structure, as shown in Figure 1, where the blue area represents the ionic aqueous solution, and the gray part is a structure made of readily available carbon fiber. The annular space containing the ionic aqueous solution has a large radius, r3 in the rotational direction, a small circular cross-sectional radius, r1 for the solution, and an outer circular cross-sectional radius, r2 for the carbon fiber encasing the solution. The density of carbon fiber is 1,750 kilograms per cubic meter, reference 2, with a tensile strength of up to 3.45 times 10 to the power of 9 pascals, reference 3. Assume that the centrifugal force is supported by the tension of the carbon fiber structure along the rotational direction. The angular velocity is omega, and the density of the ionic solution is 1,000 kilograms per cubic meter. The resulting acceleration can be expressed as r3 multiplied by the square of angular velocity, as shown in equation 2. The centrifugal force per unit length along the direction of rotation in the ionic solution is the square of the radius of the small circle in the cross-section, multiplied by pi, then multiplied by the liquid density, and finally multiplied by the acceleration value obtained from equation 2. In the hollow annular structure, the centrifugal force is calculated by taking the square of the outer radius of the small circle in the cross-section minus the square of the inner radius, then multiplying by pi, then by the solid density, and finally by the acceleration value obtained from equation 2. Using the relationship between the tension and centrifugal force of the rotating annular body, the maximum allowable angular velocity is determined as shown in equation 3, where y represents the yield strength of the carbon fiber material. Now choose r1 as 0.01 meters, which is 1 centimeter, r2 as 0.015 meters, which is 1.5 centimeters, and r3 is 0.02 meters, which is 2 centimeters. The liquid density is 1,000 kilograms per cubic meter, and the carbon fiber density is 1,750 kilograms per cubic meter. Substituting these values into equation 3, the maximum rotational speed is 58,000 radians per second. At this rotational speed, the acceleration at a radius of 2 centimeters can be calculated as the radius multiplied by the square of the rotational speed, which is approximately 68 million meters per second squared. Using equation 1 and substituting the masses of iodine ions and hydrogen ions, the electric field strength in the ionic aqueous solution is calculated to be approximately 44 volts per meter. At appropriate concentrations, the conductivity of hydrogen iodide ionic aqueous solutions can reach up to 0.85 Siemens per meter, reference 4. From electrical principles, it is known that the net output power is maximized when the voltage is halved. Under these conditions, the ionic aqueous solution can output up to 0.85 multiplied by the square of 22, which is approximately 410 watts per cubic meter. This level of power density could potentially support commercial operations. References are as follows.